Hello, everyone. Welcome to today's seminar. Today, we have Yanfang Liu from the George Washington University, and Yanfang is going to talk about deterministic statistical approach for inverse acoustic source problems using multiple frequency limited aperture data. Yanfang, thank you very much for being with us today. We are happy to have you, and the floor is yours. You can start your talk.
Yeah, thank you very much for the invitation. It is my greatest pleasure to present my work on deterministic statistical approach for inverse acoustic source problems using multiple frequency limited aperture data. So the outline of the talk is as follows. First, I will introduce the acoustic source problem, including the direct and inverse problem, and then I will present how we use the combined deterministic statistical method, in particular, the direct sampling method and the Bayesian inversion to solve the inverse source problem. And later, I will show you two examples, including the inverse point source problem using the combined method with some numerical examples, and also the extended source inverse problem, along with the numerical examples. And also, I will make a summary about the talk. So for the acoustic source problem, the setting is as follows. We assume that omega is a bounded domain with the R2 minus R bar is connected, and U satisfy the inhomogeneous Helmholtz equation, also with the thermal field radiation condition. And the K here is the wave number. It is taken from an interval Ka to Kb. And the source function f of x is in L2 space with compact support inside the domain omega. Then it is well known that the wave field U has the asymptotic behavior as here, uniformly for in all direction on the unit disk, unit circle S. And U infinity here is called the far field pattern of UXK. Then the direct problem is that we given the source function, we would like to compute both the near field UXK or the far field pattern U infinity. And for the well-known fundamental solution, phi k xy to the Helmholtz equation, it is in this form where H01 is the Hankel function of the first kind of zeroth order. Then the corresponding far field pattern, here we use phi k infinity to denote it, and it has this form. Then using the fundamental solution and its far field pattern, we can obtain the solution U to the system 1 and the far field pattern U infinity by using those two integrals involving the fundamental solution and the far field pattern with the source function. And then the inverse problem of our consideration is that we have both either the near field data or the far field data. We would like to determine the source function f of x. And here we would like to point out that in particular, we're interested in the partial data case. The partial data means that, for instance, if we have the near field data, we have the green dots are the sources, and we would like to use the measurement UXK located on a curve gamma, and gamma here could be a closed circle or just a part of the circle. If it is a closed circle, then we call the measurement data is complete. If it's just a part of the circle, then the measurement is partial data or limited aperture data. And the reason we would like to investigate the partial measurement limited aperture data is that it is very important in practical problems. For instance, in the mine detection, we can only collect the data above the ground. So the partial measurement data is of practical importance. And so like the far field data, well, the measurement is taking a part of the unit circle. But here we will need to use multiple frequency data to guarantee the uniqueness of the inverse source problem. And now let's look at how some existing methods and our methods to the inverse source problem. So currently, this is an incomplete list, and then one of the optimization problem to investigate the inverse source problem is the continuation problem, which is started by the group by Ball's group. And for the optimization problem, we need to use good initial. We need the performance of the optimization methods depends on the initial choice. But the disadvantage is that the computation is expensive. And the other method includes the eigenvalue expansion from the Eller et al. In 2007 and the Zhang et al. In 2015. For the eigenfunction expansion methods, their reconstruction could be good, but the disadvantage is that here we need to take a special step for the measurement data. In particular, like for the Eller's group, they use the Dirichlet eigenfunction expansion. We need to choose the wave numbers that is associated with the either Dirichlet eigenvalues or the Neumann eigenvalues. And same for Zhang's group, they use the Fourier basis, and their wave number is associated with the Fourier frequency. And the other popular type of method is the sampling type methods, and there are lots of investigations. For the sampling type methods, we can only obtain useful information about the unknown source, which is qualitative. But the implementation is fast, and but the disadvantage is that we will need lots of measurement data to obtain good reconstruction. Partial measurement, the reconstruction will deteriorate quickly. And recently, the Bayesian method to the inverse problem is getting more and more popular because especially for the investigation of the partial measurement data, since for the Bayesian method, it can provide useful, like more information compared to deterministic methods. So based on, inspired by these properties, we proposed to combine both the deterministic method and the Bayesian method to investigate the inverse source problem. Because first we will use the deterministic methods to obtain qualitative information of the source. In particular, is the sampling type method because it's easy to simulate the sampling type method. And then the information will be encoded into the priors of the Bayesian inversion, which will accelerate the computation and improve the reconstruction. Now let's look at the details of our methods. So first, as we said, that we would like to use the direct sampling method to start to get qualitative information of the source. In particular, we would like to get a number and an estimate of the locations of the source using both near field data or the far field data. For the sampling type method, for the direct sampling method, researchers, Ito, they investigated this method, but for their study, they just limited the reconstruction for point-like target, and with all direction or with the complete measurement data. And here we extended the method to investigate the sources, which is not point-like, but it could be in the form of exponential function, and just with partial measurement data, also with multiple frequency. So in particular, for the sampling type method, we will first choose a domain which contains the source, and then along this domain, sampling domain D, we will get a mesh, and along the sampling points on the mesh, we will define indicator function. Based on the behavior of the indicator function, we can decide whether the sampling point ZP is located inside or outside of the source function. So in particular, we will propose the near field indicator function and the far field indicator function corresponding to the near field data and the far field data. And ZP here is the sampling point. So you can see that based on the definition of the indicator function, for instance, 5, you can see that according to the Cauchy-Schwarz inequality, we will have if ZP is inside the source function, then this value is getting larger and larger, but the range of the indicator function is between 0 and 1. So when ZP is inside of the source function, the indicator function will approach +1. And if ZP moves away from the source function, then the indicator function will be close to 0. Then based on the value of the indicator function, we can determine whether the ZP is inside of the source function or outside of the source function. Then with this in mind, we can use the direct sampling method to get the numbers and also the rough locations of the source. And then this information will be encoded into the Bayesian inversion. And the details of the algorithm of the direct sampling method is as follows. First, we will collect both the near field data, or we will collect either the near field data or far field data on the partial or the full capture with multiple frequency, and then we will choose a sampling domain, assume that this contains the support of the source function, and then generate a mesh for this sampling domain. For each sampling point, ZP, we calculate the indicator function, and then use the value of the indicator function to decide the numbers of the sources and find an approximate locations of the source function. With the source information, we now consider the inverse source problem and the Bayesian framework. And so for this inverse source problem, we can rewrite it in this statistical model. Well, U equals f of a plus eta. U here is the measurement data, and f a here is the forward operator, which is just for if we have the far field data U, then we take the far field pattern of the fundamental solution. If we have near field data, then we just take this as the fundamental solution for this prediction. And A here represent the details information of the source function. So originally, based on the DSM method, we just have the qualitative information. Here we want to get the quantitative information. But to improve the performance, we will interrogate the information in the DSM into the unknown variable A. And the eta here is the noise, which is assumed to follow a normal distribution with variance sigma squared, mean 0. Then according to the Bayesian theorem, we have that the posterior distribution of A, which is the solution to the inverse statistical inverse problem, it satisfies this relationship, which says that the posterior distribution, the conditional distribution of A given the measurement, is proportional to the likelihood the conditional distribution of the measurement given A multiplied by the prior distribution of A. If we define the G to be in this form, and gamma here, and then the relationship 8 in terms of the posterior measure mu U and the prior measure mu 0, it can be written in this form, and LU here is the normalization constant. Next, we will study the stability result of the inverse statistical problem. First, we will show some properties of the forward operator f of a. So here it can be proved that f of a actually is C1, and then based on this conclusion, we can show that f is Lipschitz in A. Along with those two properties, we can prove that the posterior measure with respect to the posterior measure mu u is also Lipschitz with respect to the measurement data u1 and u2 and the Henninger distance. And for the exploration of the posterior distribution of pi a given u, in general, it is difficult to obtain the analytic expression for that posterior distribution. And most likely people will use the numerical method to get an approximate of the posterior distribution. So then the general steps are as follows. First, we will choose an initial value for the unknown a based on the results we have in the DSM, and then we will propose a move using the precondition Crank-Nixon Metropolis Hastings algorithm, and the beta here is the step size of the move. Then we compute the acceptance ratio using this formula. If the acceptance ratio is greater than some value follows a uniform distribution, then we accept the proposed move. Otherwise, we will stay at the current position. When we reach the maximum sample size, we can stop the process. Otherwise, we can just increase the superscript j by 1 and go to step 2 and repeat this process. After we obtain the Markov chain of the unknown a, then we will discard some samples and take the mean of the rest of the samples, which is called the condition mean, and this will be a point estimator of the unknown a. Next, we will use the combined deterministic statistic method to investigate the two inverse source problems. The first one is the inverse point source problem. So in particular, for the source function, we will take the source function to be the linear combination of point sources and the extended sources, which has the form of exponential function. So here we need to assume that the sources the contact support of the source function is inside the region omega. And then for the intensities of the sources, they must satisfy certain conditions. For the point source, it is either be a monopole or a dipole source. And for the extended source we consider here is just the exponential type source function. So to reconstruct the source function, we need to both identify the locations and the numbers of the source function, and also the intensities, lambda and xi. Then for the combined method, we will first use the direct sampling methods to locate the source function by taking the local maximum of the indicator function. So for those local maximizers, we will assume that they are a rough estimate of the location of the sources. And then we can also use the number of the local maximizer to be the number of the sources. Once we have the rough locations and numbers of the sources, we can encode this information into the Bayesian statistics, which will tell us the dimensions of the unknown a, and also we will take the Z0, the local maximizer of the indicator function, to be the mean value of the variable z, and then use the Bayesian statistic to investigate the distribution of the unknown a. So still, as we said before, the direct sampling method will give us the qualitative information, and then we will explore the detailed information of the source using the Bayesian inversion. Now let's look at the several numerical examples to illustrate the efficiency of our proposed method. So first, we will consider the domain omega is a square from -4 to +4. The synthetic near field data and the far field data are given by the forward operator. To avoid the inverse crime, we will add 5% noise to the synthetic data to get the measurement, both the partial and the full measurement. And then for the complete aperture, we take S1 to be from 0 to 2 pi, and S2 is just a half of the aperture, and S3 is a quarter of the aperture. So the observations, the measurement observations are taken from those three apertures, and the angles are equally distributed along the aperture. For S1, we have 80 observations, S2 is 40, and S3 is just 20. The near field data are taken on this are taken from this disk with radius 6.5, and the wave numbers is from the interval Ka to Kb, and they are also equally distributed. For the first example, we will use the near field data, and the second example considers the far field data. The sampling domain is chosen to be the same as the domain omega, which has this mesh to 201 times 201. And then for the settings in the Bayesian inversion, we assume that all the variables follow a Gaussian distribution, and the locations obtained in the DSM, they are the mean of the position variable Z. In the first example, we take f of x to be the linear combination of monopole and the dipoles, and for the simulation, we take the positions J to be those values, and the intensity is lambda and Z at those values. And here we plotted the indicator function for all three scenarios, S1, S2, and S3. So you can see clearly that the indicator function can identify both the numbers of both the number of the source function and also the type of the source function. So this is the monopole, and those are two dipoles. And then we just take the local maximizer of the indicator function to be the reconstructed positions of the source function. So even for the partial measurement S3, we can find the numbers of the sources and also the locations of the source function. But and the reconstruction of the source location are listed here. And you can see that if we have full actual data, the reconstruction is quite satisfactory. But when the measurement data are getting less and less from S1 to S3, the reconstruction might deteriorate from the exact ones a little bit. So when the measurement data is getting less and less, the performance of the DSM method will decreases. And then we will take the reconstructed positions of the source to be the mean of the position in the Bayesian inversion. And here we will take the step size for the position to be 0.05, and the step size for the intensity to be a smaller value to increase the acceptance ratio for the samples. And here in this table, we listed the reconstruction result by the Bayesian inversion. So here this part is the exact parameters we use in this example. And then for S1, the reconstruction of the intensities for lambda and C are here. You can see that they are quite close to the exact values when we have full aperture data. And the reconstruction deteriorates when the data is getting less and less. But one interesting phenomenon is that you can see for the reconstructions of the positions, previously we have the mean value is negative 2.2 and the negative 1.94. But for the Bayesian inversion, after we perform the MC method, we can actually refine the reconstructions of the positions using the Bayesian inversion. So you can see here the result is better compared to what we have in the directed sampling method. Next, we consider the a more complicated case, which is in the form of exponential function. And we still just have here, we just have two sources. The indicator function presented here. And for three scenarios, the reconstructed locations are just close to the exact ones. 2 combines 2 and negative 1.5 combines negative 1.5. And still, we can successfully reconstruct the intensities and also refine the construction of the positions. So here in this in this part, we just consider simple sources, which either be the point source or the exponential type source function. And still, we just use the direct sampling method to obtain qualitative information, and those information is interrogated into the Bayesian inversion to improve the reconstructions. Next, we will study the inverse source problem, which has the extended source, the more general case. Let's first quickly review the inverse source problem. So first, we still would like to reconstruct the f of x either from partial field data, partial measurement data, or complete measurement data with multiple frequency. And then for the extended source problem, we will still use the directed sampling method to obtain an estimate of the support of f of x. So just to get an estimated region which contains the compact support of f of x. And then we will, based on the reconstructed region B hat, we will find the dirichlet, we will find the dirichlet eigenfunction of this region, and then use the dirichlet eigenfunction to expand the source f of x. Then in the Bayesian inversion, the task is just to explore the expansion coefficient. So here, for the approximate region B hat, we will in particular just consider it to be a disk with radius r, and r is chosen by 11. The reason we choose B hat to be a disk is twofold. First, we know that the disk can easily cover the compact support of the source. And secondly, the dirichlet eigenfunction for a disk are easy to obtain. Now let's look at the eigenfunction expansion of the source function. So for the dirichlet eigenvalue and the corresponding eigenfunction, the eigenvalue is lambda and the eigenfunction is omega. They satisfy this system. And since the dirichlet eigenfunctions is associated with an elliptic self-adjoint compact operator, then the omega and the eigenfunctions will form an orthonormal complete set in L2 B hat. Then for any function f belongs to this space, it can have this expansion form, where the coefficient is given by the integral. In particular, if B hat is a disk with radius r, then we have the dirichlet eigenfunctions is Qn M1 and Qn M2. And the Jn here is the Bessel function of order n. And the Qn m, they are the m's zeros of the Bessel function Jn. Then those eigenfunctions will satisfy the Helmholtz equation with Knm is Qnm over r. Then we can get an approximation of the source function by the truncated linear combination of the eigenfunctions with n from 1 to capital N and n from 0 to capital N and m from 1 to capital M. So we will take an approximation of the source function using the eigenfunction expansion of the region B hat. It is proved by Eller in 2007 that if F belongs to the subleft space with compact support, then the omega n will form and also normalize the dirichlet eigenfunctions of B hat. And also the approximation is given by 15. Then if we take the eigenfunction, the coefficient of the eigenfunction expansion to be vector A, the inverse problem will becomes the reconstruction of the coefficients A given the measurement U. And here we would like to point out that we can choose a disk B, we choose a disk B hat because the dirichlet eigenfunction are known analytically, and you can also use other domains which contains the support of the source, such as the rectangular domain or the polygon domain. And another thing I would like to say is that besides the direct sampling methods, we can also use other sampling type methods like the extended sampling methods and the orthogonality sampling type method to find an estimation of the compact support of the source. So then once we reform this as an inverse problem of finding the coefficient A, we will use the Bayesian inversion to investigate the coefficients A. And we still have several numerical examples for this extended inverse extended source problem. Still, the measurement data are given by the forward operator, but to avoid the inverse prime, we will perturb the data with 3% noise. And the sampling region in this setting we still have is a square from -4 to +4 with 81 times 81 sampling points. And 3 actual data, 3 actual for the observation directions is taken from S1, S2, and S3. S1 is still the full actual, and S2 is from 0 to pi, just half of the actual, and S3 is a quarter of the actual. And for this inverse source problem, we will take the wave number in the DSM to be just from 1 to 3 wave numbers, and the corresponding cutoff value for the choice of the disk B hat is 0.41, 0.64, and 0.70 by trial and error. In the Bayesian inversion, we will use more numbers of wave number, and for the truncation of the approximation, we take n to be 2 and m to be 5, and in total, which means that we will have 25 terms in the truncations. The sample size of the Markov chain is we used is 120,000, with the first 20,000 examples are dropped, and the step size of the step size is taken to be 0.001. So in the first example, we will take f of x just to be a multiple of the dirichlet eigenfunction Q11, and then x belongs to this disk domain. In the first row, we have the plot of the indicator function. Here, the red dashed line represents the exact boundary of the source function, and the black circle is the reconstructed support of the source function using the direct sampling method according to the cutoff value. And then once we have the approximate region of the source function, we can use the eigenfunction expansion to obtain the coefficients of the expansion using the Bayesian inversion. And the reconstruction is shown in the second one. Here, the orange mesh is the reconstruction result, and the blue mesh is the exact source function. And the first column is the result for scenario 1, and then scenario 2, scenario 3. So you can see that for all three cases, the direct sampling method will capture the domain of the source function, and also is close to it contains the compact support of the source, and also the domain we choose is close to the exact region. And the reconstructions in the Bayesian inversion is quite satisfactory, even though we just have partial data. Next, we consider f of x to be in this form, and still the reconstruction is quite good. And but here we can notice that when the data is getting less and less, the reconstruction deteriorates a little bit. The next example is exponential type source. And here, even though we plotted the red dashed line at the exact region, here we just have a cutoff for the support of the source function, because we know that for exponential function, the domain is R2. And here the red dashed region is just an approximate compact support, where we choose the x values such that the magnitude of the function is greater than 10 to the negative 10th power, and make an approximation to the source function. And still the reconstruction we get in the Bayesian inversion is very good, but when the data is getting less, the reconstruction become worse, but still very good. And the last example we considered is a discontinuous function. F of x is this characteristic function, and the compact support is a disk with radius 0.9. For this one, the DSM can still capture the compact support of the source function. Moreover, in the Bayesian inversion, we can successfully capture the discontinuity of the source function, and still, even with partial measurement data, the reconstruction is quite good. And last, I will list the reconstruction result by the DSM method and the arrow of the Bayesian inversion. So here, I listed the exact support of the source function and the radius we obtained in the DSM for 3 scenarios. For example 1, the exact boundary is the disk with radius 0.9, and then we have the reconstructed radius as follows. And for example 2 and the example 3, as I said before, it is an approximate region. So we use B star to denote an approximate of the support. And still, for all those 4 cases and the 3 scenarios, we will capture the compact support of the source. And in table 4, we have the absolute error and the relative error of the Bayesian inversion based on the compact support obtained by the direct sampling method. In example 1, we choose the 3 times the eigenfunction. So you can see that the reconstruction is very good. It's within 7%. And so as example 2, we have a very good reconstruction. But for example 3 and example 4, the properties of the function is more difficult. We still have a good approximation if we have full actual data. And then when the available data become less and less, the reconstruction decreases. So in this talk, we use a two-step deterministic statistic approach to study the reconstruction of the acoustic sources using partial measurement data with multiple frequency. And we use the deterministic method to obtain qualitative information, such as the numbers and the approximate locations of the source. And then this information is encoded into the priors of the Bayesian method to obtain quantitative information. The combined methods inherits the merits of the deterministic method and Bayesian inversion, as demonstrated by the numerical example. And here are some projects we have done for using the deterministic statistical method to study. And in the future, we would like to extend the combined method to study the recovery of underwater acoustics wave speed, both time harmonic and time dependent, and the reconstruction of the shape and the trajectory of moving objects. Yeah, thank you.
Thank you very much for the excellent talk, Yanfang. Anyone, any questions or comments? No one has any questions or comments, I guess. Okay. Okay, then. Thank you very much again for accepting the invitation, Yanfang, and for the excellent talk. And thank you very much, everyone, for joining us today. I'm gonna see you in 2 weeks in the next seminar. Thanks and see you. Bye.
See you, professors. Thank you.
Thanks.
Bye, everyone. Thank you.
See you.